Okay, a last bit on plate tectonics. We'll do a little review later, but this will finish off our first look at the plate tectonics. Okay. Again, Red Sea, good example of an early stage in the Wilson cycle. There is ocean there, so it's not the very first step of continental rifting, but it's a fairly narrow ocean. The two sides are pretty parallel, reflecting the fact that they've just recently split apart. And we are starting to build new ocean floor crust along the bottom of the Red Sea. Again, if this keeps on going long enough, we'd go from a narrow sea to a big ocean similar to the Atlantic. Over time, as we start out with a relatively narrow sea, things can get blocked up, and so we can potentially have ocean water come in and get trapped. And so we often have a zone of evaporite or salt deposits forming along the edges. As the new sea widens, you get a more permanent connection, more normal seawater, better to keep the ocean life happy. And we've got those rocky edges from the two sides splitting apart. That's a good spot for a reef to grow on. And so we often have reef type deposits building up there. Now, eventually, again, we've got all the sand and mud, sediment eroding off the land, dead things piling up. And as we're moving away from the spreading zone, things are getting older, colder, sinking down. So eventually our reefs will tend to get buried away. And so it is common, keeping in mind vertical exaggeration, to have a buried reef along the edge of a continental shelf. There are buried reefs along the edge of the shelf off the coast of North Carolina, for example. So what? Yeah, geologists would be interested, but how does it affect anybody else? Well, a buried shallow water reef, or for that matter, a deep water reef, there are those as well. All those things growing there tends to be a lot of holes. Those holes are good for holding stuff that might be down under the ground, such as oil. Similarly, that evaporite can squish like the asthenosphere rock, move around, and so you can get blobs of salt moving up, which will form bends in the sediment layers, again, making good places to potentially trap oil. So these structures can be quite important as potential petroleum reserves. Now, of course, burning petroleum causes some other problems. We'll be looking at that later in the class. But there is economic interest consideration. We've got these on our coast. Similar structures are found, say, along the Gulf of Mexico, around Arabia, some of the areas that are major producing regions as well. We've talked about what happens when plates are pulling apart, mid-ocean ridges or rift valley zones. Talked about collision, but what if our plates are sliding past each other? That situation, the structure is known as a transform fault, and by far the most famous is the San Andreas fault, because there are lots of people around it, and it's actually up on land. The transform fault connects seafloor spreading ridges down in the Gulf of California, or Sea of Cortez, depending on which side of the border you're on, and connects up to ones off the coast of northernmost California to southern Canada. Sliding along, so what is now Baja California in Mexico, plus the southwestern corner of the state of California, US, is moving north relative to the rest of North America, and eventually, given long enough, will be colliding with Alaska. Now, it's not a perfect straight line all the way. There's zigs and zags, so you do get little bits of collision or pulling apart. But overall, this is one side sliding past each other for the transform faulting. So here are a couple of diagrams. You see here Baja in California in Mexico, plus the southwest corner of California moving along. And now given about 15 million years, Los Angeles would be next to San Francisco. No, it's not falling off into the ocean. It's moving sideways relative to the rest of North America. The middle diagram highlights the fact that there are lots of faults. It's not just a single one, but many other cracks associated with it, not surprisingly, where you have plates moving past each other. And then the right-hand bit highlights that you do have a little bit of zig and zag, so there are small-scale collision mountains and pull-apart valleys, but overall it's moving past each other, transform faulting along the San Andreas. You do get big earthquakes here, not quite as big as the ones in the collision zone, but certainly big enough to cause significant damage. Also, the earthquakes associated with our strike-slip transform boundaries are all pretty shallow in the ground. Nothing is getting shoved down underneath another, so there's nothing to go very deep. Not surprisingly, if the earthquake happens only a little ways down the ground, you're feeling a lot more of the energy at the surface concentrated to a small area than for an earthquake that's way deep in the ground, and those waves had to travel through quite a lot of ground and spread out a good deal before they make it all the way to the surface. So this is a picture showing some damage from the last really big one along the San Andreas system. So here we go. Here's a summary of things that you find at different types of plate boundaries. Our spreading zone, we have divergent motion. So these are the two sides moving apart. Our typical structure there is a mid-ocean ridge. Yeah, we got the continental rift systems as well, but mostly it's under the ocean, mid-ocean ridges. With this, we get earthquakes. These are quite shallow in the earth because it doesn't take getting too far down before you're to that big zone of hot rock rising up. Hotter, squishier rock doesn't break, doesn't have earthquakes. Also, we're pulling apart, not crashing into each other, so the earthquakes are typically not as strong. You get weak earthquakes anywhere, up to typically about medium size. The biggest earthquakes at spreading zones would be big enough to be not a good thing to have happen near a major city, but the number of major cities out on the bottom of the ocean is pretty small. So generally not much of a problem. Plenty of volcanism, but again, pretty calm. Mostly it's crack in seafloor, blob of lava oozes out, cools. Mid-Atlantic ridge, classic spreading zone, the first mid-ocean ridge to be identified. Collision zones, the two sides are converging, coming together. If both sides are ocean type crust, all that's our denser, darker rock, so not too hard to find something that's going to go down underneath. So as one plate is shoved underneath the other, we get the low point of the trench. We get melting, forming volcanoes. We get the volcanic island arc a long chain of volcanoes. Things are erupting here and there all along the chain. No pattern in the ages there. Because one plate is going down deep into the earth, then we can have very deep earthquakes. And these range up to very, very strong. Volcanoes, we have a volcanic island chain. In these collision zones, if we have volcanoes, they seem to be somewhat explosive, kind of in between your typical ocean and your typical continental volcanic system. So these are explosive enough to be dangerous. The Aleutians off of Alaska and the Lesser Antilles in the Caribbean are a couple of ocean-ocean collision island chains. Ocean continent, well, again, collision, we're converging. And it's not too hard to figure out. That ocean plate's the denser one. It's going to be one shoved down under our continent. Once again, we'll have a trench. We'll have melting. We'll have volcanoes. But over here is continent, not ocean. So instead of our volcanic island chain, we'll have our volcanic mountain chain. Again, earthquakes can be very deep because of the one plate being shoved underneath, and very, very strong. The largest earthquakes we've ever measured have been in ocean continent collision zones. Andes in South America, the Cascades in northwestern North America are good examples of ocean continent collision mountain chains. Two continents run into each other. Again, this is our less dense rock, so it doesn't shove down very well, and it has to go up. Just like two cars running into each other, you can get all crumpled up. We're going to get mountains forming as our two plates run into each other. We have big horizontal faulting as parts shoved up other parts. So much rock there in the crust that what does melt generally does not make it up to the surface. So we have our big mountains, but not volcanism. Earthquakes, shallow to medium depth, after all, tall mountains. It's ways down from the top of the mountain. And we have the roots of our crust extending down the plate with the mantle underneath it, somewhat thicker under the mountains. So this means that we do have earthquakes moderately deep down, not nearly as extremely deep as in our ocean collisions where there's an actual plate chunk that is headed down there, but deeper than you get at our spreading zones or transform faults. And the earthquakes can get pretty big. The biggest earthquake not at a trench that we have measured was near the Himalayas in the 50s. Again, not volcanic, but very tall mountain chains. Transform, that's where we have the two sides. One slides past the other. So we'll have a fault line associated with that. Earthquakes are pretty shallow, nothing's going down into the earth. These earthquakes can be up to pretty strong, not as extreme as collision, but yeah, as somebody in California, earthquakes can get bad there. Again, nothing's going down, nothing's melting, so we don't get volcanoes associated with them. San Andreas, the most famous of these. We also have those zigs and zags on the mid-ocean ridges that are little transform faults between segments of the spreading zone. So, overall picture diagram again. We have a zone of hot mantle rock rising up under the mid-ocean ridge here. As it reaches the surface, we make new rock here. Get some melting with less pressure, and then it cools. So we have the two plates spreading apart along our mid-ocean ridge. We have push out from there. We have pull from the sinking plates. We've got the mantle circulation. All of those, the the suction from broken bits. These help to move the plates. As things move out from the middle, they're getting older, colder, denser, sinking down, more sediments piling up on top of them. Eventually, collision, if it's an ocean plate, you can shove deep down underneath the other plate, and we get a trench where they meet, subduction as one plate goes under the other. We get melting in volcanoes, very big earthquakes. Continent-continent collision, not shown in the picture here. Great big tall mountains. Transform boundaries, you can see one here in this kind of zigzag in the mid-ocean ridge. The two sides are sliding past each other. Again, big zone of rising hot rock gives us the mid-ocean ridge. An area of melting where one plate goes in another gives us our volcanic island chain or mountain chain where they're all active around the same time. A narrow column coming from deeper down gives us the hot spot and a volcanic mountain chain where the volcanoes go from youngest at the hot spot, getting older and older as you go along the plate direction. Okay, so what? Well, it's kind of relevant if you want to know, are you likely to have earthquakes or volcanoes, things like that near where you live? But it turns out that having some on the planet where you live at any rate is actually probably a good thing for life. Plate tectonics provides a way of recycling material. What is buried away is not lost forever. It can be brought back up and returned to the surface. So this is important, for example, in mineral nutrients. As things die and get buried away, eventually the elements in them get cycled back around once more available at the surface. A very important example of the element cycling is with carbon. Carbon, of course, key part of living things. It's also in many rocks, most commonly as calcium carbonate. Stuff like limestone, marble, corals, seashells are made of calcium carbonate. Carbon, of course, can also be part of a gas in the air as carbon dioxide. So on the one hand, we can have carbon dioxide from the air, either chemically reacting with rocks, or maybe it's dissolved in water and then reacts with things, forming minerals. So we take carbon dioxide out of the air, turn it into rock. It can be buried away for a while, but that can erode or be heated by volcanoes or something and break down and release the carbon dioxide once more. So we've got a cycle back and forth where carbon dioxide can go into the air, into the rock, back and forth. This helps maintain a balance. In contrast, we don't have plate tectonics happening. We don't have a good way of taking carbon dioxide out. And planet Venus, represented here, although I'm not sure why they may look that blue in the picture. It's got a runaway greenhouse effect. Way too much carbon dioxide in the atmosphere, and it is unbearably hot. It's hot enough to melt lead on the surface. Not suitable for life. Here on Earth, we've got some carbon dioxide in the air. We want some so it's not too cold, but we want it to not be too much so it's not too hot either. Plate tectonics helps maintain that balance. Okay, so that's a summary of plate tectonics, how it works, what are a number of the clues, how we figured out that this is an important pattern for the oceans, and some of what effects it has, the patterns of earthquakes, volcanoes, things like that.